Okay, this chapter is about chapter 15, which is the Roy model. Okay, the Roy model is a very influential model in economics, and the model is all about self-selection. It was first developed by Roy in his analysis of earnings in two occupational sectors. And in Roy's example, the two occupations were hunting and fishing. The model assumes that individuals have some endowed skill in both sectors, but they can only choose to work in one sector, and they choose the sector that gives them the highest earnings. This model can be used to study the effects of unions on earnings, or the effect of education on earnings, or the effect of participating in a job training program. There are lots of examples of applications. Okay, this is the basic setup. So let F and H denote an individual's endowment of skills in the two occupations. And we're going to assume that the skills are log normally distributed. And you can think of talent as mattering more in the occupation that has a higher variance. So in this graph, you can see the skills here are positively correlated, that the people with high H skill tend to have high F skill, but it could also go the other way around. Okay, so it could either have positive correlation or negative correlation. Okay, denote the earnings of fishermen and hunters by the following. So the earnings in the fishing occupation is the endowment of skill times the price paid per unit of fish. Okay, so you can think of skill as like the units a person's able to produce, and similarly in hunting. Okay, so an individual chooses the occupation that maximizes their earnings. So this is really where we use our economics. Okay, this should actually be a lowercase I. They choose fishing if that gives them the highest earnings, else they choose hunting. There's going to be some range of F and H over which they're indifferent. Okay, we can ask, okay, let's denote the joint density of skills in the population as G here. And we can ask, what's the average amount of fish caught by people who choose fishing as their occupation? Okay, that's E of F given YF greater than YH. Okay. So here we're integrating over the range, all the possible range of H and F. Okay, so H ranges over the whole range, 0 to infinity, but we're conditioning on F being in this range. So that's why F only ranges over this partial range. Okay, and we need to divide by this. So the density is actually this quantity here inclusive of the denominator. Okay, and we need to divide by that because the density has to satisfy the property that integrates to 1. Okay, then if M is the total population, the total supply of fish in the population is going to be the number of people times the average amount of fish that a fisherman produces times the proportion of people that choose fishing as their occupation. Okay. All right, now let's look at how we're going to get the parameters of this model. Okay, so we're going to look at the implications of self-selection for mean earnings in that occupation. Okay, we're going to denote log earnings in the fishing occupation by Y0 and log earnings in the hunting occupation, this should say hunting, by Y1. Okay, so earnings is assumed to depend on some observable characteristics. So these could be like age, gender, whatever you think might matter, height, for fishing and hunting, eyesight. And then these are just some unobservable factors. And notice here that the prices are fixed in the population, so they'll just be absorbed into the intercept when we estimate the equation. We'll assume that these residuals are joint normally distributed. So that's really assuming that the skill distribution was log normally distributed. So this is the variance covariance matrix. And we can define a correlation coefficient in the definition of correlation coefficient is the covariance over the square root of the two variances. Okay. So this is just another way of writing. Sometimes it'll be convenient to write it in terms of correlation coefficient. Okay, so we need to uncover these parameters. These are all the parameters that describe the model. Okay, if we just estimated a model of the probability of choosing the hunting occupation, okay, that's going to be the probability hunting yields the highest income. Okay, and we could, given that epsilon's normal, epsilon 0, epsilon 1 is normal, then the difference is going to be normal. Okay, and here this is the standard deviation of epsilon 0 minus epsilon 1. Here, that's what it is. So if earnings were assigned at random, then the average earnings would just be x beta 1 and x beta 0. But the problem is people are selecting into the earnings that gives them, or into the occupation that gives them the highest earnings, so it's not random assignment. And this self-selection is going to create an endogeneity problem. Okay, so let's look at the earnings in Sector 1 for people who chose Sector 1 as their preferred occupation. Okay, so the expectation of error term, we can write this way. This here just means D equals 1. Okay, this means that you chose Sector 1 as your preferred occupation. And here I'm just dividing by sigma 1 and multiplying by sigma 1. All right, and we're going to derive an expression for this term, but we need to have, this is a normal random variable, standard normal, and this is also normal random variable. Okay, and to derive an expression for this term, we're going to need to have some equations for the mean of one normal random variable conditional on the truncation. Here, see, this normal random variable is truncated from above. So we need the mean of one normal random variable conditional on the value of another. Okay, and we can use this formula here. I mean, actually, we don't need this one. So E of U given V greater than C. So V is truncated from below. Okay, this is the expression. And if everything is standardized, then its variance of V is going to be 1. Okay, so now let's look at this example. So here I just replaced this epsilon 0 minus epsilon 1 with psi to make the notation simpler. Okay, this is the covariance of epsilon 0 and epsilon 1 minus the variance. Okay, so that was applying that formula from the previous page. We can write it this way, and in terms of correlation coefficient, we can write it this way. Okay, this term is going to be less than 0 because this is a standard normal and we're truncating it from above. So you can think of it as just like drawing from a standard normal and only keeping the ones that are below some level. It's going to be less than 0. Okay, and this is just factoring this out. All right, so this term, remember, is less than 0. So that means that this mean earnings given self-selection is going to be less than E of Y1 with random assignment. You know, this should actually have conditional on X here. Because we're saying either conditional on D equals 1 or just conditional on X. Okay, so if this is positive, then this overall expression is negative. And in that case, this is less than this. But if this term here is negative, then this overall term is going to be positive, because remember, this term is negative. Okay, and so this first case is called positive selection, because with selection, the earnings are higher than they would be otherwise. Okay. Similarly, we can do the same sort of operations for the Fisherman equation and also derive conditions under which you get either positive, here I remembered the conditional on X. So you either get positive selection or negative selection. Okay, could we have negative selection in both sectors? That would mean that the mean with selection is less than the mean if randomly assigned to that occupation. Okay, it turns out that's not possible. Okay, why? Because the variance of this psi, okay, this has to be positive. Okay, so really I should put a greater than 0 here. And that implies that either sigma 1 squared is greater than sigma 1 0, or sigma 2 squared is greater than sigma 1 0. Okay, or both could be true. All right, but that implies either rho is less than sigma 1 over sigma 0, or rho is less than sigma 0 over sigma 1. Okay, so that means you cannot have negative selection in both sectors. You could at most have negative selection in one sector. Okay, and that's all from the fact that this variance has to be positive. Okay, how do we estimate this model? Okay, let's write the original equation here. Notice what I'm doing is I'm basically adding and subtracting this term. Okay, so this term here is identical to this term. It's just plugging in for what these things mean. Okay, this error term has conditional mean 0 by construction. Okay, so we're going to estimate this equation by including this control function here. All right, and the expression for the control function is this. And this term on the front of it, this is constant for everybody. So this will just be estimated as a coefficient in the regression. So we're basically going to include this as an additional regressor. This is actually called the Mills ratio. And then this is just going to turn out to be the constant term on that regressor. Okay, why could we not just estimate the model ignoring selection? Well, the reason is because you only see y1 for d equals 1 individuals, and the mean of the error term, conditional on x and conditional on d equals 1, is not equal to 0. Okay, so we need this to control for selectivity bias. Okay, it's sometimes called lambda, which is the Mills ratio. Okay, this actually varies with I. I mean, everything y, this has an I, this has an I, this has an I, this has an I, okay? It's just not showing it for, keep notation a little simpler. Okay, and similarly, we can do the same sort of thing for the y0 equation. Control function will look a little bit different, but here's the Mills ratio, okay, and here's the equation we would estimate. Now notice this depends on this quantity, which is unknown, but we can get this quantity here from the probit estimation. Okay, so here's a two-step estimation approach. First, you estimate a probit model using only data on which sector people are in. From that, you get these estimates here, and you can form these two Mills ratio, lambda 1 and lambda 0, for each person. Now estimate the y1 and y0 regressions, including these control functions. From this, we'll get estimates of beta 1, beta 0. Okay, from the probit, we only got the difference in beta standardized by sigma. But from the earnings regression, you actually get beta 1 and beta 0. Okay, and you get those constant terms in front of the control functions. Okay, it turns out that you can go a step further and estimate regression equations. Okay, and don't worry about this. This is a little bit more advanced, but you can actually separate out all these sigma parameters. But you need to estimate a couple more regression equations that relate to the second moments of y0 and y1. All right, now once we have all our estimates, what can we do? Okay, well, we can do what's called counterfactual analysis. So we can say, what would the earnings of fishermen be had they chose hunting as their occupation?